Hello everyone, welcome back. Today we are going to discuss about Dish-Jozsa algorithm, so which was proposed by David Dish and Richard Jozsa in 1992. So whereas in Dish algorithm you are having a function, okay, f of 0 comma 1. So we need to check whether it is constant or balanced, right? So but whereas here you will be having the same function, but it is for n qubits. This is only for 1 qubit, but this is for n qubits. We need to check the same condition whether the given function is constant or balanced. So what I have given here, we have a function f of x takes n bit number. So the function can be only giving two types of behavior. One is constant and another one is balanced. So you already know constants give the same output for every x, whereas balance gives 0 for half of the inputs and 1 for other half. So our job is to figure out which type it is, whether it is constant, the given function is constant or balanced. So for a classical computer, we need to check at least half of the inputs to whether to know whether the given input is constant or not. So but in quantum computer, we can find the answer in just one try. So this will be done using superposition, right? Superposition. So now this is the circuit for Dish-Jozsa algorithm. Okay, so we are having an ancilla. This we call it as ancilla. So this is helper qubit, and we are having n registers. So this we call it as registers. So if you check here, all are the n registers starting with the base get 0 and applying Hadamard for n qubits, and after that you are applying oracle box, and then again you are applying Hadamard gate. So after that you are measuring the given function is balanced or not. So at psi naught I am talking. At psi naught the equation is will be like this: get 0 0 0 so on n, okay, so on n. So with the tensor product with minus, so we won't take, okay. So now what I am doing is nothing but I am doing the tensor product. So if I do the tensor product of h get 0 h get 0 h get 0, if I take two terms, let us see, I am trying with two terms. Already you know these equations, get 0 h get 0, right? So if I take the tensor product, 1 by root 2 ket 0 plus ket 1 will be for h of ket 0. Again h of ket 0 if I take, I am doing the multiplication 0 0 0 0 1 1 0 and 1 1. I think this is clear. So I can write this in generalized form, that is nothing but 1 by root 1 by 2 summation of x belongs to 0 comma 1 square. So square represents, this 2 represents 4 outputs: 0 0 0 1 1 0 1 1. So if it is 3, you know 3 zeros, 0 0 1, like that it will be. So if I try for n is equal to 3, so if I apply Hadamard gate for 3 qubits, so I will end up getting 0 0 0 0 1 0 1 0 0 0 0 1 1 1 0 0 1 0 1 1 1 0 and 1 1 1. I think this is clear. If you check here, 1 by 2 root 3 power 3. So x belongs to 0 comma 1. I have written the power, I am changing the power, so please check. So as n increasing, so this number is increasing, right? And this is also same. So this is the generalized equation for h of n get 0 with n qubits, right? So now the task is we need to apply oracle box. At ket psi 2 we need to apply oracle box. So if I apply oracle box, you already know the formula, minus 1 of f power f of x ket minus. So now I have done that. I'm writing the generalized equation because we cannot show all the n qubits, right? So this minus from now on, after applying oracle, this minus can be ignored because it won't work on the main qubits, right? So now apply Hadamard gate for each qubits. If you apply Hadamard gate for each qubits again, h of n ket x, you need to apply Hadamard gate for n qubit for x. So if you do that, what you will be getting, h of x naught, h of x1, h of x n minus 1 until n minus 1, because the index is starting from 0. So what I am doing is nothing but I am writing h of xi, for example h of ket 0, let us solve 1 by root 2 ket 0, this minus what I am writing is nothing but minus 1. If it is 0, if the index is, if the qubit is 0, ket 1, right? If the qubit is 0, obviously it becomes plus 1. So plus plus, there will be no change. If it is, for example, if it is ket 1, the indexing will be, this power will be changed and it will be resulting minus here. Here you will be getting minus 1. So that's why I am writing this for some shortcut representation. I think this is repeated. So from now on, from, if you look here, if you do for h of ket 0, you know the xi, it is 0 because here it is 0. So I will be getting the same result. If you do it for 1, minus 1 power 1 is nothing but you will be resulting minus. So same way I am done for these qubits. Please look. So I have expanded h of 3. So this is how the expanded qubits looks like. And now what I have done is nothing but I have multiplied, I have done the tensor product. So if you observe here, the thing is, when 1 comes, this coefficient is coming. 1 comes in the qubit or 1 comes in the superposition, this coefficient is coming, right? So if I add up all those coefficients, I will be ended up getting x2, x1, x1 plus x2, x0, x0 plus x2, x0 plus x2, x0 plus x1 plus x2, right? So now what I am doing is nothing but, so that I am taking that as the dot product, okay? So the dot product I am taking it. So I will explain what is dot product. So I can write these as the generalized equation. So if I take minus 1 dot product x dot z ket z, so I can write this generalized equation for x h into x, okay? So if you do integrate with that, already we are having this and we are integrating this, you will be end up getting this equation, okay? So here f of x is there and I am adding the powers, okay? So this is nothing but dot product, you need to remember. So what is the dot product? So sorry, I have written for y. So z, this is z, this is z. So for example, I am already having x some values, right? So I am applying Hadamard on this, right? So if you apply Hadamard, for example, z basis is 0 1 0 1 1, let us think. So what does this dot product do is nothing but x0 is 1, x1 is 0, x2 is 1, and z0 is 0, z1 is 1, z2 is 1. So what does this dot product do? x0 into z0, x1 into y1, x2 into y2. If you do it, 1 you will be getting. So if you take the mod 2. So now you need to take the mod 2 if the sum is even. If you look here, if the sum is even, for example 0 2 4 6, if the sum is even, the result will be 0. If the sum is odd, the result will be 1. So in this particular case, x dot y is 1. So minus 1 power 1, already you know, minus 1, right? If it is minus 1 power 0 plus 1, that is the simple trick you need to remember. Now what I am doing is nothing but I am taking the amplitude of ket 0 power nothing but for n qubits. So if I take the amplitude of n qubits, if I consider the amplitude is 0, all zeros, okay, all ket zeros. So x dot z always get 0, because if one is 0, other amplitudes are 0, the resultant will be 0. So if you do that, I will be end up getting this equation. So 1 by 2 power n summation of x belongs to 0 comma 1 n minus 1 power f of x. So now I think this is the final equation. So if f of x is constant, you need to check. So if f of x is constant, so minus 1 power 0. For example, f of x is constant, I am checking for f of x is equal to 0. If I check it, so if I substitute in this formula 1 by 2 power n summation x belongs to 0 comma 1 power n minus 1, and f of x is 0, I am considering, I am taking the constant. So 1 minus 1 power 0 will be 1, but it is for n qubits, right? So on it will be there, that is nothing but 2n. So already we are having 1 power 2n will be cancelled, the resultant will be 1. So if you check for 1 also, you will be ended up getting minus 1. So always if the amplitudes are 0, the constant function is lying in between plus and minus 1. So probability of measuring all zeros is always 1. Now if f of x is balanced, in this case you check. So I need to take, for example, 1 by root 2, 1 by 2 power n, get minus 1 power 0, 1 minus 1 power 1, same way vice versa I need to go. So if you substitute all those things, minus 1 power 0 will be plus 1, minus 1 power 1 will be minus 1, minus 1 power 0 will be plus 1, again so on. If you add up all those things, you will be getting 0. 0 into anything will be 0, right? So what you are getting is nothing but, if f is constant, you are getting plus or minus 1. So if f is balanced, your amplitude is getting to 0. So probability of measuring is 0. This is about Jozsa algorithm. If you are having any doubts, let me know in the comment section. Thank you.